Hello everyone, welcome back. In this video, we'll be discussing about the third problem of yesterday's biweekly contest, sorting three groups. The problem is a bit easy problem. It's just that the statement of the problem is a bit difficult to understand, but once you understand the statement, because of the constraint, the problem is easy to solve. In this video, we'll be looking at how to solve this problem in the brute force manner, and then we will be looking at one harder follow-up wherein nums.length will be less than equals to 10 to the power 6 or 10 to the power 5. So if you are here just for the harder version, you can skip the entire video until that piece. All the timestamps are there in the description down below. You can move back and forth. So with that, let's get started. The problem states that you are given a zero indexed array nums of length n. The numbers from 0 to n minus 1 are divided into three groups, 1, 2 and 3, where number I belongs to nums of I. Now you are allowed to perform the following operation any number of times. Basically you can pick a number x and change its group. In other words, you can change the nums of I to any value you want. Now a new array result will be constructed using the following procedure. You will sort the numbers in each group independently and then append the numbers in the following order. You will add all the numbers of all the sorted numbers in group 1, followed by all the sorted numbers in group 2, and followed by all the sorted numbers in group 3. Now following this, you will prepare a result array, and if the result array is non-decreasing or increasing, the given array nums will be a beautiful array. You need to return the minimum number of operations that you need to perform to make the given array nums a beautiful array. So a lot of things going on. Just to reiterate this part, we have been given numbers from 0 to n minus 1. Each of them has a group, and we have been given which number belongs to which group initially. For example, if this is the array which we have given, it says 0 belongs to group 2, 1 belongs to group 1, 2 belongs to group 3, 3 belongs to group 2, and 4 belongs to group 1. Now we can change the group of any number in this from 0 to n minus 1 to any group we want, and finally after doing so, we will see if the resultant array result will be non-decreasing or not. If it is non-decreasing, then array nums will be a beautiful array, and we have to modify the array minimum number of times such that the given array nums will be beautiful. So let's take one example. Let's say this is the array 2 2 3 2 1 1 2 1. Now if you don't do any operations and see if the given array nums is a beautiful array or not, how to figure out whether this is a beautiful array or not? The definition is you will prepare a result array, and if the result array is non-decreasing, it is a beautiful array. So let's prepare the result array. Result array can be prepared by sorting the numbers in each group independently. So this is group 1, this is group 2, and this is group 3. So if you see, there are 3 numbers in group 1, 5, 6 and 8. In group 2 there are 0, 1, 2, 4 and 7, and in group 3, 3 is the only number. Now if you sort this is the sorted numbers, and you have to append them in this order, 1 followed by 2 followed by 3. So you will say 5, 6, 8 followed by the sorted group 2 followed by the sorted group 3. Now you can see this array is not a non-decreasing array or an increasing array, and hence the given array num is not beautiful. So let's do some changes. Let's say you changed the group of 3 from 3 to 2. You change the group of 6 from 1 to 3, and similarly you change the group of 7 and 8 to 3 as well. Now after doing this, let's see if the array becomes beautiful or not. So how to check that? Again the same trick. You will sort the numbers in each group independently. So number in group 1 is 5, number in group 2 is 0, 1, 2, 3 and 4, and number in group 3 is 6, 7, 8. Now you have to merge them in the order 1, 2, 3. So you will say you will first put 1 and then put 2 and then put 3. Now you can see this array is also not sorted, and hence this num was also not beautiful. Let's look at one last example. Let's say you also change this 5 to 3. In that case, group 1 will be empty, and group 3 would contain 5, 6, 7, 8. And if you merge this, so group 1 will be empty, and then group 2 will be next, and then group 3 will come, and you will have 5 here in group 3. And you can see this group is sorted, and hence the given array nums is a beautiful array. Now to make this array nums beautiful, you have to perform 1, 2, 3, 4, 5 operations. Now similarly, you might have other possible nums array which is beautiful. You have to figure out among all such which one requires minimum number of operations. So that is the problem statement. Now how to solve this? Let's make some observation. So notice that the numbers, there is just one way in which the number can be sorted in increasing order, and this way is the sorted array from 0 to n-1 itself. So every time the array will be sorted if the groups in which they belong is sorted. In other words, if nums is sorted, we can say that the given array will be sorted. If nums is not sorted, the resultant array will also be not sorted. We have seen that twice in this example. So the problem statement now reduced to figuring out how we can make the given array nums sorted. Basically, we will have some 1s before, and then we will have some 2s, and then we will have some 3s. This is the way in which we can sort the given array nums. So the reduced problem now is we just need to figure out the minimum number of operations in which we can make the array num sorted, and we can like ditch all of these conditions completely, right? So if you understand this, if you haven't reached this state during the contest or after solving the problem, I would encourage you to pause and try to think of the problem again. Basically, now you just need to figure out how many operations are required to sort this array. That's it. Or how many minimum number of operations are required to sort this array. So let's look at it. Now, as discussed, we have to make this array sorted. Now, if you want to make this array sorted, the array would contain some 1s first, followed by some 2s, and then followed by some 3s. Right? That is the way in which you can make the array sorted. Now, there may not be any 1 as well, or there may not be any 2s as well, or there may not be any 3s as well. So basically, each of these consecutive sections might be empty as well. In other words, we may not have 1 at all in this array. This array might simply be like this, and this is also a sorted array, right? And in a similar fashion, we may not have 2 at all, so we can have everything as 1, right? And this is also a sorted array. We don't have 2 and 3. So basically, we need to figure out the point until which everything will be 1, and the point until which everything will be 2, and after that everything will be 3, right? So we just need to figure out the best these 2 point. Let's denote these 2 things by I and j. We just need to figure out the most optimal value of I and j such that we can sort just that the number of operations is minimized. Now let's just take one small example. Let's say I is 2 and j is 5. So let's say I is this and j is 3, 4, 5. Let's say j is this, right? In other words, what we are saying is everything before I will be 1, everything from I to j will be 2, and everything from j to n will be 3, right? Now, how many operations are required to make to achieve this configuration? So basically, we need to make this 2 as 1, 1. So basically, 2 operations are required here. Then we need to make everything here as 2, so we need to remove this to 2, make this to 2, so 2 operations are required here as well. We need to make everything to 3, so we need to make this 3, make this 3, make this 3, so 3 operations are required. So in total 7 operations are required to achieve this configuration. In the similar fashion, we can try out every possible values of I and j and just take the minimum across all of them to get the answer, and that will be the optimal answer, because we are trying out every possible configuration, right? So the pseudo code for that would look something like this. What we will do, we can simply iterate over I and j, all possible values of I and j, right? Note that j can start from where I ends, so j can be only from start of I. Now I can start from 0, it means it is possible that there is no 1 at all, so in that case I will be here, and in that case we will say there is no 1 at all in the given array. Similarly, j can be n minus 1 as well, or sorry, j can be n as well, and we will say there is no 3 at all in the given array, so this will be inclusive, right? Now once you go through all the possible values of I and j, we will simply put everything before I as 1, everything between I and j as 2, everything after j is 3, and we will count how many operations are required to achieve this configuration, and we will simply take the minimum across all such configuration to get the final result. Now what is the time complexity of the entire solution? Time complexity would be order n cube, because we have 3 loops inside this. So first loop for I, second loop for j, and third loop for figuring out what is the count of elements, and this also takes order n time to fill the elements with 1, 2 and 3. So this will have order n cube time complexity, and even this order n cube will pass because n is up to 100. So this order n cube will also pass the given time constraint and can be accepted, accepted solution as well. Now let's say we need to optimize this further. Let's say n was not 100, instead n was 1000. So in that case n cube will not work, but n square might work. So can you reduce this n cube solution to n square? I would strongly encourage you to pause and try to think if you can reduce this n cube to n square by yourself. So notice there are 3 n's. First n is coming from I, second n is coming from j, and third n is coming from the fact that we are trying to iterate over the entire array to figure out what it takes to achieve this configuration, or how many operations we need to make to achieve the configurations with this particular I and j. So can we reduce this loop completely? The answer is yes. How? Notice what we are doing here. We are simply figuring out how many elements are there up till I which are not 1. Similarly, we are figuring out how many elements are there from I to j which are not 2, and similarly how many elements are there between j and n which are not 3. So instead, if we can figure out how many elements are there which are 1 in this range, how many elements are there which are 2 in this range, how many elements are there which are 3 in this range, we can simply subtract it from the total number of elements in this range and get how many are there which are not equals to 1, 2 or 3, right? So to figure out how many ones are there in a particular range, the simplest thing you can do is use prefix sum. So you can simply maintain a prefix sum of 1, 2 and 3 and answer all the 3 questions. So let's look at the solution. So basically we are trying to remove this entire thing with a constant time operation, so that we can reduce this order n of this particular loop. And what we have said is, for this we will simply figure out how many, if this is I, this is j, we will simply figure out how many ones are there in this range, how many, if let's say there are 0 ones in this range, you will simply say you require 2 operation, because you want everything to be 1, right? And you are saying that there is no 1 at all, so you require 2 operations to make this 2 as 1, right? So, and in the same fashion you will say, okay, how many 2's are there in this range? So you in this particular case there are 2 2's, so you will say I require 2 operation because I have 4 elements, 2 are already 2, other 2 we need to change. And in the same fashion you will say how many 3's are there in this range? The answer will be 0, so you require 3 operations because there are 3 elements, none of them is equals to 3, so we need to change everything here. Now we can just simply build prefix sum like this for 1, 2 and 3. So basically there is no 1, so 0, no 1, 0, no 1, 0, 0, 0, 0, and the first one we get here. So number of ones until this is 1, number of 1 we again get 1, so number of 1 until this is 2, number of 1 until this is 2, and number of 1 until this is 3. Now in any range, let's say you have to answer how many ones are there until this, you will simply say 0. How many ones are there until this, you will simply say 2, and so on and so forth. In the same fashion for 2 and 3 we build a prefix sum, and now let's say you have to figure out how many 2's are there in this range. You can say I know there are 4 2's up till this point and there are 3 2's up till this point. So in this range there will just be 1 2, right? And in the same fashion you can answer the query for 3 as well. So in 3 you need to figure out how many 3's are there after this. So you will say I know there are 1 3 until here, I know there are 1 3 until here, so in this part there will be 0 3, right? So hope you got the solution. So the pseudocode would simply be modified like this. We will simply build this p1 p2 p3 sum, and then we'll say these are the number of element which are not equals to 1, so we need to convert all of them. So total number of elements were I, these many were 1, so number of elements which are not 1 is I minus this. Similarly total number of elements were j minus I in this particular range I to j. Number of elements which are equals to 2 is p2 sum of j minus p2 sum of I minus 1, and we can just subtract these two to get number of elements which are equal to which are not equals to 2. In the same fashion we can get number of elements which are not equals to 3 and sum them all up to get exact same count that we are getting from here, and we can simply take the minimum across all such count. Now the complexity of this solution is just order n square, because you can build this p1 p2 p3 in just order n time outside of this loop itself. So we have reduced our n cube solution to order n square, but let's say the constraint is even higher. Let's say n is now less than equals to 10 to the power 5 or 10 to the power 6. So even this n square solution will not work now. So we need to optimize this further. Now how will you optimize this? So from this point you will not be able to remove one of these loop. Why? Because the entire premise of this solution is, if you know I and j, or if you know at which point 2 will start and at which point 3 will start, then figure out then try out all the possible combination and figure out the answer. But if you don't try every possible combination, you might not get the best result out of this. So either you have to do some magic wherein you will say, okay, I know 2 will start from here and I will figure out what is the best possible answer if 2 will start from here. Basically I will not say where 3 will start, but I will just find out what is the best possible answer if 2 will start from here. And similarly you can try out every possible I and get the minimum, right? So that is the basic approach we are trying to take. Basically we are trying to now reject this I as well from our loop, and we are saying, we will simply say I know 2 will start from here, now give me what is the best I can do, right? So just to tweak this thing a little bit, let's say we are saying 2 starts from here, right? Now what will be the next element? The next element can be either 2 or 3. So I will just say, okay, get me the best value if the next element starts with 2, get me the next best value if the next element starts with 3, because these are the two possible choices for this element, right? It can't have anything else. Now based on which one is minimum, you will just take that one and return the answer for this particular element. So basically we are trying to reduce the problem into further sub problems and trying to apply the recursion here. So if you see, we have been asked, okay, what is the best number of best result or minimum number of operations if 2 starts from here. Now what we are asking is, okay, give me what is the best result or minimum number of operations required if 2 starts from here or if 3 starts from here, right? So if we have f of I comma val, basically it says give me the minimum number of ways in which I can fill the remaining array after I such that the current value is val. If you can figure out the value of this, we can figure out we can use this same recursive function to calculate for the rest of the array as well. So let's look at the recursive function itself. So we'll start from f of 0 comma let's say 1. So there are 3 possible choices, right? You will start from f of 0 comma 1, or you can start from f of 0 comma 2, or you can start from f of 0 comma 3, right? And if you start from f of 0 comma 1, it means that you are saying give me the minimum number of operations required if the 0th element is 1, right? For if you are starting from f of 0 comma 2, you are saying give me the minimum number of operations required if the 0th element is 2, and similarly f of 0 comma 3 denotes give me the minimum number of operations required if f of 0 is 3. Now from f of 0 comma 1, where can you go? So if you have filled this with let's just get rid of this. So if you have filled this with 0, or if you have filled this with 1, then what are the choices for the next element? Next element can be 1, 2 or 3, right? Anything can be the next element, right? But if you have filled this with 2 instead, then the next element could be either 2 or 3. We can't fill 1 here, right? So we will simply say, for if you have filled 1 here, we will simply figure out what is the value of f of 1 comma 1, f of 1 comma 2 and f of 1 comma 3. Based on whichever is minimum, that will be the best possible choice for f of 0 comma 1. In the same fashion, you will figure out the value for f of 0 comma 2. You will figure out the value of f of 1 comma 2 and f of 1 comma 3. You will not figure out the value of, you will not take the value of f of 1 comma 1 here, because you know that current element itself is 2. So after 2 there can be either 2 or 3. 1 can't be there here, otherwise the array will become not sorted. In the same fashion, for f of 0 comma 3, you will just figure out f of 1 comma 3, and whichever is minimum across these two will be the value here, whichever is minimum across these 3 will be the value here, and for this one the value will be simply f of 1 comma 3. Now just one more thing, let's say you fill 1 here, so you just need to also make sure that what is the value here, because you have filled 1 here, so you will have to apply one more operation here. So based on whatever is the minimum, you will simply add 1 to that, because you have filled 1 here and this 2 are not equal, so you need to apply one operation here. Similarly for this one, whatever is the minimum, you will simply add 0 here, because if you fill 2 here, 2 and 2 are equal, you don't need to apply any operation here. In the same fashion, you will add 1 here based on whatever is the minimum, and this will be your answer for f of 0 comma 3, and finally you will take the minimum across these 3 to get the final answer, because it doesn't matter whether you start from 1, 2 or 3, you just need to return what is the minimum number of operations required. So you can just take the minimum across all of them and that will give you the minimum operations required to to make the array sorted. So how will the pseudocode look like? Pseudocode would be very straightforward. We will have two things in our function, index and val. Index denotes which index we are currently filling, and val denotes what is the value of the current index, right? So either you can go from 0 to n, or you can come from n to 0. So this pseudocode is to come from n to 0. Let's say you fill 3 here. So previously in the previous element you can put either 3 or 2 or 1. In similar fashion, if you put 2 here, in the previous element you can put either 1 or 2. And in the same fashion, if you put 1 here, the previous element will be 1. There is no other choice. So that's what we have done. If the current element has this particular value, the previous element can have anything between 1 and val, right? And based on what previous element is, you will simply figure out what is the minimum operations required to make this index end, or make this particular array end at this previous element, and add 1 or 0 based on if you need to do anything for the current element as well or not. So if current element you have filled val, so if current element is not val, you have to add 1 because you need to make it val. If current element is not 1, you don't need to do anything else, right? So the entire time complexity of this entire solution is number of states multiplied by what we are doing in each state. So number of state would be what we are doing in each state. In each state we are iterating over 1 to val, and what is the maximum value of val? 3, right? So inside each state we are doing 3 operations in worst case, and number of states is number of different values of index, which is n, number of distinct values of val, which is 3. So inside each one we are doing 3n operations. So in total, the entire complexity of this entire solution will be order n, which will pass the constraint where n is less than or equal to 10 to the power 6. So just to reiterate this part, we started with order n cube solution, which is the brute force one, and then we saw that we can remove the innermost loop with just prefix sum. We did that and reduced the complexity to order n square. After that we said that okay, if we need to reduce this further, we need to remove this loop as well. In other words, we should be able to answer if I have started with a particular element, then what is the minimum number of operations required to fill all the elements starting from that particular element. So that's what was needed. So from that we thought of okay, we can use recursion, because if we are able to figure out what is the minimum number of operations required to fill everything starting from I, where I is equals to value, then we can simply say that okay, I will try to fill the next element based on the current element. If current element is 1, the next element could be either 1 or 2 or 3. If the current element is 2, the next element could be either 2 or 3. And similarly, if the current element is 3, the next element can only be 3. And based on that, I will just take the minimum across all of them, and I will add 1 or 0 based on what I have filled here. So if I filled val here, and if val is not equals to the given value of nums of I have to add one operation, because I need to make this to val as well. So one operation will be required here, otherwise no operation is required. So that's why we will either add 1 or 0 based on if nums of I is equals to val or not. And we can simply memorize it to make sure that we are not computing the same state again and again. So in total there are this many states. In each state you are doing this many computations, so the entire complexity is order n. So if you have watched till this point, I would encourage you to at least code the order n square and order n solution by yourself, because that's what will give you much better clarity and will help you understand if you didn't get any piece in this solution. So I would encourage you to code this entire thing by yourself before moving ahead. So next we'll be looking at the code. So in the code I have done bottom up just to, so the top down solution will be straightforward. We have to just write a function that does exactly this. So I haven't shown the top down solution, instead I have shown bottom up solution. So if you remember, we have discussed multiple times in this channel how to convert top down to bottom up. So we just need to simply cover the base case, and then from base once we have the base case ready, we can simply add everything else inside the for loop of bottom up. That will be it. So that's what we have done. We covered the base case. Base case is basically if there is no element at all, then in that case you like there is no way at all to fill. So there is just one way to fill this, right? There is no other valid way, and there is no operation required as at all. So that's why we have put dp of 0 as 0. Other things are very huge. And after that, we have simply put the exact thing that is there inside this recursive state. So we will try everything from 0 to I, and we will see if current element is equals to I, then we will add 1, otherwise not 0, and dp of previous, because we know that previous is already calculated, right? So once you have done this loop, you will have everything for the previous state. So basically I am not maintaining a 2D array here, instead I am just maintaining a 1D array for value. So 1D array which contains just 3 elements, 1, 2 and 3. Basically how many operations are required? If I have to end with 1, how many operations are required? I have to end with 2. How many operations are required if I have to end with 3? Why I haven't stored the entire array, entire 2D array? Because to calculate the value at I plus 1, or to calculate the value at I, you just need the value at I minus 1, nothing else, right? So that's why we reduce the space complexity as well. So in this particular solution, the space complexity was order n, but in this case the space complexity is just order 3, which is constant. So why we are able to do so? Again, because we know that for calculating the value of I, we just need the value at I minus 1. So we just keep track of what is the value at I minus 1 in this dp, and keep on updating this dp after we have calculated the value at I. And finally, as we discussed, we will simply return dp minimum of 1, 2 and 3, because it doesn't matter where we will end, we just need to return the minimum number of operations required, right? So hope this entire solution makes sense. If you have any doubts in any of the solution, feel free to post them in the comment section below. I would be able to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.